Good morning. I'm Yuriy Shmaliy from the University of Guanajuato, and my presentation will be about optimal and robust state estimation, batch and recursive approaches. It is well known that optimal estimation of signal characteristics and system models is required to formalize a posteriori knowledge about undergoing processes in the presence of noise. It's important that every kind of noise requires its own optimal estimator. It's not about the robustness, but the optimality we achieve for each kind of noise. I will consider two parts of the problem. First, optimal state estimation, including optimal batch and the Kalman recursions. Optimal unbiased or maximum likelihood FAR filtering, then the unbiased state estimator. As the second part will be devoted to robust state estimation. Mostly all the results of this presentation is just an overview of my recent book on optimal and robust state estimation, finite impulse response FAR and Kalman approaches, and you can find many results in this book. So what is optimal state estimation? The optimality we understand as a process to achieve the minimum possible estimation error. So the estimator must be the best of all other estimators. It's not only about linear problem, also nonlinear problem, and in the modern view, the estimator also must be quite robust to be practically useful. The motivation of to design new kind of state estimator beyond the Kalman filter was presented by Yashvinsky many years ago. He said that the limited memory filter appears to be the only device for preventing divergence in the presence of unbounded perturbation in the system. It means that we must rely on the smallest possible piece of information to produce the optimal result, and this will guarantee the best robustness of the filter. In discrete time, this means that we need to consider the state space model, which is extended to some horizon or from some past point, say, as a point M to the current point K, and the number of the points is N. And if you formalize this model with all the matrices, and the noise also is formalized with the statistics, and we also do it, and the conditions that noise is zero mean, it's a regular supposition for this kind, that we can think about the optimal estimator. To design any estimator we need to operate with some performances. In the case of it is a filter, we use four general estimates related to the process in question. So it is the a priori estimate, which ignores the current point and also the a priori error covariance. It is a posteriori estimate that includes the current point and also the estimation error covariance, so at this same point. Kalman proposes the following strategy. Let's start with zero, formalize all the initial conditions at zero, and then go ahead recursively. But this estimator strongly relies on the complete knowledge about the system. System must be linear, noise must be wide Gaussian, and we need to know the statistics of the noise QK, QK, and RK. So the question arises, how can we do it? How can we know? How can we formalize all this knowledge? especially when the system is time varying. So we need to do it at each time step. The resume is that if the initial conditions x0, p0, the initial state and the covariance are not known exactly, the initial errors will affect estimates possibly over long transients due to infinite impulse response. And if the noise statistics are not known exactly, not defined or defined imprecisely, the estimate will be either biased or noisy. To overcome this problem, there is a method that is called the batch method, so that it is actually the original our desire to create any filter. The filter must have some impulse response, some transfer function. If you use a Kalman filter, it doesn't respond to this question. What actually is the impulse response of the Kalman filter? What actually is the transfer function? Nobody knows. So that to answer these questions, we should extend the state space model to the averaging horizon of some endpoints, represent the model with a more complex way, so it's segmented model, specify the vectors and all the vectors to be of the form of the block form, and then repeat the derivation procedure once again to arrive finally to some optimal result. And then, of course, finds a way to compare to the Kalman filter. So let's consider the optimal batch FAR filter and discuss its relation to Kalman recursions. The cost function for the batch optimal FAR filter is that we need to minimize the error covariance, the trace of the error covariance by changing the gain of the filter. The gain is a collection of the coefficients of the impulse response, so that if we will apply the orthogonality condition, which means that we stay at the optimal point, and we can obtain two unbiasedness constraints. So it means that if we further need to remove bias, that we need to also to embed these conditions into the filter structure. And describe all the matrices related to the noise statistics. It's a very important point that the batch estimator doesn't claim that the noise covariance must be diagonal, so it should not obligatorily be wide, but still Gaussian. As the batch optimal FI filter appears in this form, where we have the database collected in the vector Y capital, and the control signal collected in the U capital on the horizon from the point M to the point K, and the optimal gain for this filter, H, this gain, now has all the necessary information about the system and the noise, so that we can expect that the result obtained from this structure satisfies the Yuzhvinsky conditions that it should be more robust. Now let's say that in this new formulation, the error covariance matrix of the filter PK has the universal structure. So it has the initial point here that collects the initial conditions here, and two block matrices associated with the system noise and the measurement noise, and we have also three residual matrices which describe the power or effect of the residual on the error covariance of this structure. But what's more important is that if you derive the filter in this way, the batch algorithm this way, and then converting it to the iterative structure, that this structure uses the common recursions. The recursions are represented with algorithm 4 here, and the optimal FAR filter algorithm a posteriori and iterative is given by the algorithm 5. So we have the first proof that the Kalman filter operates as the iterative procedure of the optimal FAR filter that is a batch estimator. Now, let's present two intrinsic errors of the OFAR and the Kalman filter. So that if we are able to set correctly the initial conditions, we start, of course, very close to the actual behavior of the process. But if we are not able to do so, then we should expect for some transient, and in the transient range can be very, very long in case that the model is very inertial. Another problem with the optimal estimator is that if we fail to fill correctly the noise covariance matrices Q and R, then we have two principal problems. First, the output can be either more biased, so it is about the regular arrow, or more noisy. In both cases, the results show here, so the noisy output, the more biased output with respect to the optimal output that relies on the correct knowledge about noise. So this is a problem. How can we do it? Uh, how can we extract information about noise practically? It's a real problem. There are several adaptive algorithms to do so, but ideally, if you want to have an optimal estimate, we should know both matrices exactly. Now let's consider how can we solve the problem if you would like the optimal estimator to be also unbiased. The unbiasedness embedded into the optimal structure gives the maximum likelihood, and so let's consider this filter. The cost function for the optimal unbiased algorithm is this one, so that we still need to minimize the trace of the error covariance matrices, but subject it to the unbiasedness constraints. The unbiasedness constraint must be created for both for the database, for our measurement, and also for the control signal. So we have two conditions here. And the cost function can be created if we include the Lagrange multiplier term related to the unbiasedness condition into the derivation structure. And this structure returns us the estimate, which is very similar to the optimal estimate, but in this case, we have another gain matrix for the batch filter. The error covariance still has the same universal form, but here we lose the initial condition term. It is a very important conclusion that the unbiasedness embedded to the optimal structure removes the requirement for the initial conditions. And we have here also only two residual matrices, this one and this one. But the most important thing is that when we convert the optimal unbiased FAR batch filter to the recursive form, that of course represents the iterative algorithm, that we conclude that recursions, which are this one, are not common recursions. So that the optimal filter with embedded unbiasedness is served but another algorithm than the Kalman filter. And the Kalman filter is thus not unbiased filter, as was previously thought. It's very simple to show that ignore some terms here that this algorithm converts to the Kalman filter, but only under the conditions that we do not lose information about the initial state and initial error covariances. So the first conclusion that appears from the derivation of the optimal unbiased FAR filter and conversion to recursive form that the Kalman filter is not an unbiased estimator. It is an optimal estimator. Now let's discuss the properties of state estimators in the batch and recursive form. The optimal FAR filter is the most general among other optimal linear estimators. It becomes optimal unbiased or maximum likelihood if you advance the unbiasedness. It converges to the unbiased FAR filter by ignoring noise, but two other conclusions that follow from this one, that there is no back way. We cannot go from the unbiased FAR filter to the optimal unbiased and from the optimal unbiased to the optimal filter because at each step we lose some information. The batch FAR estimate can be computed using Kalman recursion. So the Kalman algorithm is associated with the optimal optimal batch estimate. The batch optimal unbiased FAR estimate can be computed using recursion different from the Kalman recursions. And this is a very important conclusion to know that once again, that the Kalman filter is optimal. It's not optimal unbiased. The problem that we meet here are associated with the required information. The optimal FAR filter requires all information about noise, about the model, and about the initial values, and what's more important, that the filter must match the model exactly. And as a conclusion, it is not protected against different kinds of errors and is not robust estimator. It is more robust than the standard Kalman filter because it operates on the finite horizon of data points. So it ignores old errors, but nevertheless, it's not robust. The optimal unbiased FAR filter ignores the initial values, but still requires information about noise and thus is not sufficiently robust. Better robustness is offered by the unbiased FAR filter, so that let's go on with this solution. Unbiased FAR state estimator. The general strategy of this unbiased estimator is that let's start with some point, past point M, and consider this horizon and define the estimate as a point K using some procedure that means that we just need to follow the unbiasedness condition. So that if we use the batch form in a very short form and produce the estimate at M plus K minus 1, where K is the number of the states, then also iteratively we can go to the current point, and this is sort of the Kalman filter, but which ignores the initial conditions and completely ignores information about noise. All transients in this filter are limited with horizon lengths of n points. It's important that the horizon length for this filter must be optimal to minimize the mean square error. And if n optimal is not defined imprecisely, the estimate will be either biased or noisy. The cost function for this filter is very simple. Because we would like to have an estimator that is more robust than the optimal or optimal unbiased estimator, we just need to track the mean value of the process. Trying to track mean value and then minimize the mean square error on some optimal averaging horizon. From this cost we obtain this estimate with respect to the model, it gives two unbiasedness constraints, and from the first constraint, we obtain the batch UFAR filter, which is shown here. The estimate of the filter is equal, absolutely the same like for the optimal and optimal unbiased filter, but the gain function is different. The gain doesn't include any information about noise. It ignores the initial conditions. So it's sort of least squares, Gauss least squares, but on the in state space and derived for the FAR filter. The error covariance has a universal form where we also do not see the term which collects the initial values and where the residual matrices are specified in this way. Now about the iterative computation in the case of UFAR filter. This is an iterative algorithm which starts from the first point which is n, which must be optimal minus 1. So there is some sort of that interval. And then recursions of this filter are very simple recursions. They are simpler than in the Kalman filter. This filter also has some problems. It means that we need to specify the horizon in the optimal way. But first, let's consider the difference with the Kalman filter. The UFAI filter doesn't depend on the noise statistics, also ignores the initial value. So it is not so precise like the Kalman filter. And this green line shows, in this example, shows the mean square error of the UFAR filter when we consider the scale with beta, which represent the error in the noise covariances. So because noise is not included in the algorithm produces the constant value of all the errors in the noise covariances, unlike the Kalman filter that increases errors to the left and to the right, producing either more noisy estimate or more biased estimate. So that there is only within the very short region of the errors that the Kalman filter outperforms the UFAR filter. Beyond this area, the UFAR filter is more accurate, and this is a very important property for practical applications when we do not know exactly the noise statistics. Now about the effect of errors in the averaging horizon. When we are lucky enough to set n optimal, then the root mean square error ranges very, very close to the Kalman filter. The difference is very small, it can be ignored. But if we are not, then errors also grows up to the left and to the right. But within the range of from 50 to 130, that is about 30% of the error. The UFAR filter demonstrates almost the same error, so it is quite accurate filter for practical applications. The properties of this filter. The UFAR batch filter and its recursive form belongs to the class of Gauss least squares. Advantages. It doesn't require the noise statistics, initial error statistics, and initial state. It is more robust than the optimal FAR filter and the Kalman filter under disturbances and uncertainties, whatever it means. It is less sensitive to noise than the optimal FAR filter and Kalman filter, so that it's more robust estimator. Disadvantages. The batch has the computational complexity n squared. The iterative algorithm has the computational complexity n capital and but using parallel computing. So modern computational techniques, the UFAR filter can work as fast as the Kalman filter. and has a computational complexity unity, like the Kalman field. Now, let's go on with briefly with the robust state estimation. Our real life is full of perturbations, disturbances, uncertainties, and other annoying factors from the influence of which the estimator must be protected and hence robustness. This picture shows different kinds of influences on the estimator, beginning with unknown noise, impulsive noise, model uncertainties, environmental, industrial effects, initial values, temporal uncertainties, where a lot of factors affect the estimator, and so that if an estimator is not protected against these factors, that we should expect for extra error at the output. How the mismodeling occurs? When we say that every time we say that the estimator must match the model, but if you cannot describe the model correctly with some certain order, we should expect for some errors in the model. Also, if sudden changes like shocks and jumps affect the system, we also have some problem in the output. Therefore, the idea of robust filtering was formulated in this way. Let's think that we have some regular behavior of the process, say that we have all the errors staying at the minimum point, at this point. And let's think that the error cannot exceed some maximum point. If we tune the filter to the minimum, then we go with the optimal estimate. And if we tune the filter to the maximum, then this mode is said to be robust. This picture illustrates in a very simple way the difference between the optimal and robust estimate. When we stay here and the arrow goes up, then the output arrow, the output of the estimator grows up and may cause even divergence in the filter. But when we tune to the maximum and then arrow reduces, then we have two self-compensated effects. So arrow becomes smaller, but arrow of the tuning becomes larger, so that as a result we have this output that represents the model, the robust estimate. There are several general designs of robust estimators, and let's start with the H2 FIR filter. All these solutions were found in the frequency domain, so that the process and the process must be stationary, and the estimator must be also stationary. The cost function for the a posteriori H2F filter means that we just need to minimize the transfer function from the input to the output, and from this procedure extract the gain for the filter. The gain is this one, and it has two parts: the homogeneous gain HA, and also the filter estimate obtained through this gain with the error covariance in the general structure, where we have all the residual matrices specified. So the only difference with the optimal filter is that we have now another gain, but this gain is supposed to be more robust. The same procedure applied to the optimal unbiased filter gives another gain, this one. Once again, this filter is very close to the optimal filter, but with a more robust gain. And we now can outline the properties of the H2 FIR robust approach. In one Gaussian environment, the batch H2 FIR filter is equivalent to the optimal FIR filter. The recursive H2 filter is equivalent to the Kalman filter only in wide Gaussian environments. But unlike the Kalman filter, the batch H2 filter can operate with full error covariance matrices, so that it takes into account the correlation properties. That's more important for practical applications. In non-Gaussian environments, the beige FAR filter, H2 FAR filter appears to be more robust than the Kalman filters naturally because we pursued the robust criteria. H infinity FAR filter has another cost function, this one. Here we minimize the transfer function between the energy in the input and energy of the arrow at the output. And this gives us another solution, which involves the computation of the linear matrix inequality. This lemma formalizes the boundary lemma for filtering. And this is a suboptimal H infinity filtering algorithm, which means that to extract the robust gain from this linear matrix inequality, we must solve it with all the matrices specified and finally arrive at the robust H infinity algorithm. But this algorithm can also be combined with the H2 algorithm to have finally the more robust H2 H infinity FAR filter, which is represented with this algorithm. The property of H infinity are the following. This is a robust filter, which minimizes the maximum estimation errors for the maximized disturbances, so that if you have the solution for the maximized disturbances, then we expect for more robust output of this filter. It gives more robust but less accurate estimates than the optimal estimator. And the general point is that the higher robustness is achieved at expense of optimality. Therefore, it is less accurate. We have two more robust solutions. The first one means that we can minimize the peak arrow at the output for the maximum energy in the input of the arrow. This solution has this cost function, another energy to peak lemma, and the algorithm is also a bit different. So that let's just summarize the properties of this filter. The robust energy to peak filter minimizes the maximum estimation errors for the maximized energy of disturbances and uncertainties and all other kinds of errors. It gives a more robust but less accurate estimate than the optimal estimator. This filter is used when it is required to minimize the maximum estimation error in the estimate for the maximized error energy. And when it is required to maximize the peak estimation error to the maximization peak disturbance, another solution is used. Let's go on with this. That's all. I do not present this solution in this presentation. Several words about applications. This is a real picture how the robust tracking works in two modes. When we use the optimal filter, the arrow grows up with an increase of the arrow. And the robust mode produces this flat result, which is a bit less accurate at 0 point, but it is flat, so it's much more accurate for the maximized errors. This picture shows how the robust UFAR filter outperforms the Kalman filter in tuning the periodic, quasi-periodic behavior of the process. This practical experiment was made, if I'm not mistaken, in Germany. The robust UFAR filter was embedded into the mother robot, and it had shown much better results than the extended Kalman filter, and with the conclusion that the estimator is much more robust. This shows the application of the robust filter to improve the multi-MEM scenario measurement unit, and it shows that The error was achieved at the minimum possible way using the UFI filter in contrast to the Kalman filter. And this experiment was made in China in the design of space model mobile robots. It also shows that the extended a finite impulse response robust algorithm performs much better than the extended Kalman filter. Summary. The optimal state estimation approach is the most general in the batch form for linear models. It becomes the unbiased FIR filter by embedding the unbiasedness and becomes the unbiased FIR filter by ignoring noise. The common filter algorithm solves the optimal FIR filter and is thus optimal. The optimal unbiased FIR filter gives a maximum likelihood estimate and has recursions different from Kalman recursions. The UFIR estimate is computed by the unique iterative algorithm, so that the most robust estimator among all other linear estimators. Methods of robust FAR state estimation are used when the system operates under disturbances, uncertainties, other factors, so that we just need to have some result more stable in real, say, in industrial environments. We have several robust filters. These filters improve the result for each particular situation in each particular special case. But once again, let's state that all the robust solutions that we obtain using in the frequency domain are a bit less robust than the unbiased FIR filter that completely ignores noise and the initial conditions. Among all the solutions, this filter has the highest robustness. And that's actually all. Thank you very much.